All right, hi there. This is the first video about a very new thing we're going to do in this class called derivations. And so I want to give you a sense of what those are and introduce some basic concepts we're going to need to construct these. So we'll start here with the slides and then we'll transition to some stuff on the chalkboard to sort of illustrate some of the concepts. So here's the basic idea. Let me start off with this quote from Leibniz, German philosopher. And he says this, he says, "I feel that controversies can never be finished unless we give up complicated reasonings in favor of simple calculations, words of vague and uncertain meaning in favor of fixed symbols. When controversies arise, there will be no more necessity for disputation between two philosophers than between two accountants. Nothing will be needed, but they should take pen in hand, sit down with their counting tables, and, having summoned a friend if they like, say to one another, 'Let us calculate.'" So Leibniz had this dream that just as accountants can agree just by calculating the books, so arguments and controversies can be figured out by coming up with a system that just lets us calculate whether or not an argument is good or bad. And something like that's the idea behind these derivations. Let's introduce what's going on with these. The basic idea behind derivations is this. We're going to break up arguments into smaller sub-arguments where the validity of each sub-argument is obvious. I'll give an example of that in just a second. This will, the hope is, make the reasoning involved in an argument obvious. We'll see step by step how we get from one part of the argument to the next until we finally get to the conclusion. We will produce what's sometimes called gapless proofs, where no assumptions are left unstated. We show how from the premises we can get to the conclusion via steps that we all agree are logically sound. Here's an idea, or an example rather, of how this might go. Consider the rule below, which we might call modus ponens, or MP. It says, if you know that A arrow B, that is, if you know that if A then B, and you know that A, then you can conclude that B. And that should seem obvious to you, I hope, and if it's not obvious, you could do a truth table and convince yourself that that argument is in fact valid in sentential. So we've got a rule that says whenever you know that premises of those forms, those two premises of those forms, so that is, whenever you have something of this form, you can conclude something of that form. Now let's think how that might apply to a particular argument. Suppose we've got an argument like this. P, if P then Q, if Q then R, therefore R. How could we convince someone that that argument here is valid, given that they accept that this rule, modus ponens, is a valid rule? Maybe you can think about how you might do this. Here's the basic idea. You say, well, suppose all of the premises are true. All the premises here in this argument are true. We want to know if the conclusion is R is true. Well, from P and P arrow Q, that is the first two premises, we know that we can establish that Q is true by our modus ponens rule. It has the right form. P arrow Q, P, therefore Q. But now we know Q is true. And from Q and Q arrow R, we can establish R, again by that modus ponens rule. And so, the premises establish the conclusion. That is, the truth of the premises allows us to derive the truth of the conclusion, in this case by the rule modus ponens, which we know is valid. So the argument itself is valid. We've used this rule here to convince ourselves that this argument over here is valid. So the basic idea behind derivations is that we're going to introduce a set of rules similar to modus ponens and a formal method for writing down the derivation, so we don't have to sort of do it in English as I did on the last slide. Let me just back up one. We're going to write down a formal method so we don't have to write things out like this in this blue box here for writing down the derivation. And note something about what we're doing here. We're going to be able to complete these derivations even if you don't know what the symbols mean. That is, the modus ponens rule works even if you don't know that the arrow means if then. As long as you know that something of the form A arrow B and A allows you to derive B, you can complete the derivations without knowing the meaning of the symbols. That's what this says. Even if you don't know that A arrow B means if A then B, you can still apply the rule MP, or modus ponens. And for this reason, derivations are sometimes called syntactic proofs. That is, they're proofs of validity that depend not on what the well-formed formulas mean, but only on the pattern of symbols, the syntax, the way in which the symbols are organized. So that's what we're moving towards. But before we can do that, we need to be really clear about something called argument forms and substitution instances. So I want to work through these slides, and then after this, I'll show some examples on the chalkboard. So what are argument forms and substitution instances? Well, let's go back to our rule MP. It has the form A arrow B, A, therefore B. And consider what I'm calling over here argument 1. Not P, arrow not Q, not P, therefore not Q. I hope you can see that there's a similarity between the rule modus ponens and what I'm calling argument 1. In particular, argument 1 is what we're going to call a substitution instance of the MP argument form, or the modus ponens rule. What's that mean? A substitution instance of argument form A is any argument that is obtained from A by consistently substituting well-formed formulas for letters in A. So let's think how that works in this case. Argument 1 is a substitution instance of modus ponens because we can substitute not P for our letter A. So not P occurs here, and A occurs here. A occurs here, not P occurs there. And we can assign B to not Q in both places. And when we do that, we go from modus ponens, the rule, to argument 1. That is, by replacing A consistently with not P and B consistently with not Q, we go from MP to argument 1, and that's just what we mean when we say that argument 1 is a substitution instance of MP. Another way you can think about it is think of MP as written sort of not with letters like A and B, but instead with shapes. MP says, whatever's in the square, if you have something of the form square, arrow, circle, and you also have square, you can derive circle. So in this case, our square corresponds to not P, and our circle corresponds to not Q, and we can see how this form is reflected in argument 1. So here's some questions for you to think about. Are these substitution instances of modus ponens, the three things below the question here, 1, 2, 3, are those substitution instances of modus ponens? Maybe pause the video and think about what you think the answer is before I reveal it. All right, so the answer is that all three of these are substitution instances of modus ponens. The first one is one that we just saw. We have not P being assigned to A and not Q being assigned to B, and when we do that, we end up with this argument. The second one, our A formula is P and Q, and our B formula is not R. And when we make that assignment to MP, we end up with this substitution instance. And finally, for the last one, P arrow Q is what we've assigned to A, and P arrow R is what we've assigned to B. And again, when we make that substitution uniformly, we end up with this argument here, this substitution instance of modus ponens. Let's try another one, slightly more tricky example of substitution instances. This is a different argument form. We're going to call it MT for now, or modus tollens. It's also valid. Perhaps you remember that from our truth tables in Sentential. It says, if A, then B, not B, therefore not A. And so we want to think about the same question as we asked before. That is, are the arguments below substitution instances of MT, of modus tollens? I want to pause the video before I give the answer to this first one. Okay, what's the answer to this question for this first argument? The answer is yes. This argument here is a substitution instance of modus tollens, or MT. Why is that? Well, we've assigned A to P, so it becomes P here, and it becomes not P here in the conclusion. And we've assigned B to the formula Q, so it becomes Q in this instance and not Q here because the not's built into the form. So this argument here, this first argument, is a substitution instance of modus tollens, or MT. What about this one? I want to pause the video and think about this before I give the answer. Okay, in this case, we don't actually have a substitution instance of MT. And that might seem surprising to you, because it might seem like there's something about this second argument that is similar to the first one. After all we did is we exchanged the negated formulas for the unnegated formulas. So why does this second argument not count as a substitution instance of MT? Well, think about it this way. There's nothing we can assign to A that will, when we replace it, uniformly result in this formula, or this argument down here. That is, suppose A here is assigned to not P. Well, then we get not P there, but then when we assign this A, not P, we get not P. So if this were a substitution instance of MT, this right here should have two negations, but it has none. A similar thing is true for Q and not Q. And so this is not a substitution instance of modus tollens. The true substitution instance of modus tollens would look like this. Here, A has been assigned to not P, and so in the conclusion, A is still not P, and we pick up an extra negation from the argument form itself. A similar thing is true of not Q. Now you might be asking yourself, hold on, isn't Q the same as not Q? And isn't P the same as not P? And there's a sense in which they are the same. The sense is this: both Q and not Q are equivalent to each other. They always take the same truth value. But Q and not Q are not the same formula. After all, Q is a simple atomic, whereas not Q has two negations and then an atomic. And since these are syntactic proofs, proofs that don't depend on meaning but only on form, we rule out this middle argument as a substitution instance of MT. This, however, is a substitution instance of MT. Eventually we'll show how we can convert formulas of this form, not Q, to formulas of this form, Q. But for now, the important point is that while the last argument counts as a substitution instance of MT, the middle one does not.